Okay, so for the agenda today, we're going to evaluate some of the market trends that are leading to both the growth in data size as well as complexity. We'll talk about some of the solutions that have been proposed in the industry. We'll also identify a solution that we've been researching and show you some preliminary results, as well as those people who might be interested in participating in some early testing of this new technology. We have an opportunity at the end of this, if you are interested, that we can connect with you and perhaps get you early versions of this technology for testing. So I think for those of you who perhaps have sat in on our webinars in the past, I think it's good to start with, how are we trending in terms of the driving forces and why is the complexity of the data growing? And Scott, we've talked about this a lot, but Moore's Law is still alive and well. And in fact, the race for ever more powerful supercomputing facilities is ongoing and will probably continue through my lifetime.
Oh, easily. And, of course, what this does for people who are doing computational fluid dynamics or other physical simulations with wide length scales or time scale variations, it just means that your data sets get larger and larger. And in fact, as we've been tracking this for over a decade now, the size of the data sets, the largest data sets, tracks very well with the Moore's Law. So they've been doubling every 18 months, just like computing power has.
And with the move towards GPUs and other computational platforms, it's amazing, the level of parallelization, and Moore's Law not only is going to be in effect, but I suspect we're only going to be limited by our imagination soon, and so people will start to look at extraordinarily complex systems. And once we start to get to a more complex system, you really have to have different strategies for evaluating results. And that's one of the reasons we're trying to stay ahead of this curve.
Yes.
So with that, we wanted to get an idea, if you look at your typical workflow and the visual exploration modes that you're in, we want to see kind of where you sit. And so we're going to quickly ask a quick poll. Same thing, we'll leave this open for 45 seconds or so. So when you think of the different modes, what kind of things do you look at? You can select all that apply. So do you primarily look at slices through fluid domains? Are you looking at feature extraction, for example? And we'll go ahead and leave this open for just a while longer. We're a little over, or just about 30% or so, over 30%. And we like to cut this off at about 70. So you still have about 25 seconds or so. And you can choose all of the above, which basically means check on all of them. Okay.
Now, this is pretty consistent. We're seeing, a large number of people that will do slices and look at a series of slices through the domain or isosurfaces. That's consistent with what we've seen in the past.
Yeah, and we think about when you think of isosurfaces, well, we're seeing a lot of people apply are things like Q criteria and other ways to look at highly vertical flow, very complex flow. Okay, I think we're at 70% here. We're going to go ahead and close the poll. And let me just quickly share those results. So as Scott pointed out, it looks like for the most part, slices, isosurfaces, and stream traces are the most common ways people evaluate and interrogate results. Although it's there is a substantial portion that are doing feature extraction.
Yeah.
Okay, so let's continue on here. We'll get into the meat. So in addition, we talked briefly about data size and complexity. One thing that we've also seen is that in addition to looking at much larger cases, for those of you who are looking at a 10 million cell model, we also have people who are looking at tens, or if not hundreds, if not thousands of solutions. In that case, it's a more parametric study where, parametric study I think is used in one context and is often misunderstood. Any change in a parameter is really a parametric study. And Scott, we've talked about changing everything from your turbulence model to code to mesh. All of these things contribute to the parametric nature of the data?
Yeah, it really depends on what you're trying to evaluate. If you're a code developer, or, for instance, the high lift prediction workshop is one we've looked at before. In that case, they're trying to evaluate how well codes and turbulence models work on a particular flow field to predict the lift of an airplane in landing configuration. And so they had a lot of parameters there related to the type of code being run and the techniques used and the turbulence models, and whether it's transition models, grid resolution. So that would be a form of parametric study. On the other hand, more often than not, people are trying to evaluate the behavior of physical systems.
Right.
And those physical systems have control systems in them, and like an airplane would have an elevator and aileron for roll control and pitch control. And so right. Each of those have settings that are the parameters that you would evaluate the performance over.
And so the tool that we've developed is Tecplot Chorus. We're not going to talk about that here today, although I think we just wanted to, in the context of large data, it doesn't have to be a single file. It can be large, can be a set or a collection of CFD files.
Yes, and in particular, in the lower part of that slide you see there, talks about extracting data from all of your cases or a large set of your cases, or exploring cases simultaneously. So now, instead of looking at 100 million cell case, you may be looking at 200 million cell cases. So that's equivalent to 2 billion cells in terms of the amount of memory and compute power required to do the visualization.
And those are two things we're going to talk about here in context. So when we think about the data processing pipeline, and this is an area where we've been watching, as Scott said, for at least the last decade, and we've identified 3 main bottlenecks, and certainly there are others that are kind of sub-bottlenecks, so to speak. Mm-hmm. But we've talked about the data storage concept. I mean, this is most data, whether it's a physical spinning disk, as you see here, or a solid-state disk. The capacity is certainly doubling every 12 months or so.
Right.
But the data read speeds are doubling every 36 months.
Right. For the physical hard disks, that's how it's working, and it's called Kreider's law. And the capacity is based on the areal density of the dots on the disk, the magnetic dots. But because it has this head, and the disk is spinning underneath it, the speed at which it can actually pull the data off is based on the lineal density, the density along that line that it's reading. And so that is much slower, of course, than the areal density, much smaller. And so it's only doubling every 36 months.
Mm-hmm. And certainly we've done some internal testing, and even on my machine, we do some kind of benchmarking and profiling, and for most of the data that I'm looking at, data I/O, even on my local machine, tends to be the bottleneck.
Right. We've done this. You can see here that the network bandwidth is doubling every 16 months, 18 months, something like that. It tends to go in chunks, but even when we're reading off of for the local area network, when you're reading off a file system right. out on the network somewhere, it's still the disk read bottleneck that's limiting the rate at which you can get the data off the disk. Right. It's not the network at this point.
And we think about going back to Moore's law and the original intent of Moore's law, and think of just the changes in computational resources around what's available for the CPU GPUs. I thought that was kind of cute, the Intel Pentium. I don't know. I'm sure some of the people here in the audience remember the Pentium, but maybe some others don't. But in terms of GPU performance, I mean, this is actually something that, of course, is always driven by video games more than anything. But Sony just recently announced that they're using GPUs for their PlayStation 4, and they showed a demo of looking at 1 million particles dropping from the sky and bouncing off the environment. So, this is just every 18 months, the CPU, GPUs are just getting faster and faster.
CPUs have been doubling in performance every 18 months. The GPUs are probably faster than that. It maybe is sort of slowing down to be even with the CPUs, but for the longest time they were doubling every 10 months or 12 months.
And so in that context, at the end of the day, all of this processing comes down to trying to understand that the results that I have make sense, and am I answering the question, my engineering question. Is ideally, you're going into this process with, okay, I'm going to run a simulation, or I'm going to take test data, and I'm trying to answer a question. And what we're looking at in this pipeline is how does one get from basically that data to the answer, a meaningful engineering answer and a decision.
And as you look at this, remember that the amount of data, the rate at which you can read data off the disk is improving. It's doubling every 36 months. Yeah. But the size of the data you're trying to read is going with Moore's law. So it's doubling every 18 months. So it's growing faster than you can get it off the disk.
So for context, we wanted to ask the question in the context of your bandwidth. Now, we had a comment, if you're using an iPad, apparently you cannot participate in the poll, and we apologize. But you're more than welcome to chime in via the question and answer or chat if you choose to. Well, let's go ahead and take a look at that, and we'll go ahead and take a look. So what we're asking for, when you think about the bandwidth that you have available to get to your CFD results, are these being accessed via the internet? Is this over a high-speed broadband, the LAN, or is this just sitting on your local machine? And Scott, that's something over the years, we have a fast file server here at Tecplot, and we put almost everything on our storage area network, and it's relatively fast.
Yeah. I mean, there's a certain amount of parallelism in that system, and of course it has very high speed connections to the network. It looks like most people actually have their data locally, either on the LAN or on the local machine, which means that you have pretty good network speeds. Yeah. And in your case, almost certainly the bottleneck is going to be in how fast you can get the data off the disk.
So as Scott pointed out, it looks like 53% or so people who are attending here today have their disk local or data local, which is not inconsistent with what we've seen. So, okay, let's continue on because we're going to actually get into the meat of it. So, again, I think hopefully we can contend at this point that having the data on a disk is posing a bit of a data transfer rate problem, especially given the fact that data I/O is only doubling every 36 months. And Scott, I think the next slide might be better to go into detail on that.
Yeah, let's go ahead.
Which is basically the consequence of these trends, that the current visualization architectures will slow down as time goes on. This is something sometimes called the Redshift.
The Redshift is the result of each component along the way in the pipeline is slower than the previous one. So the hard disk is the slowest to improve. The CPU, or even if you start talking about the individual cores on the CPU, are the fastest to improve, and the gap is getting larger as you go on. And so what you see here in this plot is three things. There's the time at which if you look at the green line, for instance, on the bottom, the time it takes to read, to actually transfer the data over the network is actually reducing, because remember the data is growing with Moore's law, doubling every 18 months. And the data we found indicates that the local area network is actually improving slightly faster than that every 16 months. So it takes less time as we go forward into the future to actually transfer that data over the network. On the other hand, the red line shows that it takes more time to get it off the disk, and if you add those two together, you can get that orange line for if you have data on the local area network, which indicates that there's this minimum, right? There's the time at which the time to actually transfer the data to the CPU and start doing the visualization was the best it ever was, right around 2005. And if you're using a traditional visualization code, your time has the time it takes you to get your job done has been slowing down since 2005. According to this data, I think you could argue that maybe it's later than that or even earlier, but the trend is certainly there.
So in that context, I know that there's a number of research groups that are looking at ways to address this problem. We're certainly not the only people out there who understand that this is a problem. So maybe we ought to spend just a moment talking about some of the strategies that are being evaluated to address this problem. And maybe we'll start with some of the hardware improvements, and specifically around parallelization of data.
Right. There are several options for doing parallel file systems. And if you can think about it, if the problem is the hardware actually, moving the disk underneath the head, then if you have multiple heads, multiple spindles, you can speed things up. And that's what this basically means. You have you increase the number of spindles, and you can get faster transfer rates. This is kind of the approach that's being followed at a lot of the large data centers. The problem with it is, in order to actually achieve what you need to achieve so that your performance is improving over time, that the number of spindles you have, the number of hard disks you have in the parallel file system has to grow exponentially. And we all know that you can't double the number of hard disks indefinitely. That's not going to happen. So this is an important solution. It's something that on the large data centers they should be doing, but it's not going to overcome the problem by itself. There's also people looking at more elaborate systems, the solid-state disks.
Sure.
Maybe even more, holographic memory or whatever. Those things the solid-state disks are available. At this point, they don't appear to be both fast enough and cheap enough to really replace the traditional systems in most places. But maybe in the future that will change. We'll see.
Well, and another strategy I know that's, in fact, quite a few people are starting to evaluate is the in situ visualization model, where, in fact, the data never goes to storage. You're looking at it as on the fly as it's being calculated, which, for some problems may actually be okay, but there are some significant limitations when you think about in situ visualization and the implications to exploration and discovery.
Yeah, I mean, the implication is that if you need to look at the data in a different way than you've done, you have to rerun your simulation. Well, if your simulation takes a few minutes, that may not be a problem. But if you're running a CFD code, for instance, a direct numerical simulation of turbulence that takes a month, that's kind of silly, frankly, and so it doesn't give you the opportunity in those cases to really do a thorough investigation of your problem, and it assumes you know everything ahead of time. And so, as you say, it's important in certain cases and probably part of the mix. It's something people should be doing, but it's not the ultimate solution.
And I think you hit on the key point here, which is if you know the answer already going into the simulation, you know exactly where to look, then it works great.
Yeah.
But then I would ask, why are you doing the simulation? Because you kind of already know the answer. So that's it really depends again on what are you trying to do, and that's an area people are investing energy. And similarly, there's a lot of strategies for parallelizing the actual rendering. This idea of parallel visualization, where you're taking advantage of multiple nodes and actually, in some cases, partitioning the image that is shown on screen. Again, it's a viable strategy for some situations. And it does require a lot of hardware.
Yeah, this is especially useful when you really have a rendering bottleneck. And there are cases where you just have, tens of millions, hundreds of millions of individual triangles on your screen, and that will require you to do something like this. But that's usually not the case, frankly. Usually, at least with physical simulations like we're dealing with, that's the bottleneck is not the rendering. Now it might help with the reading a little bit because it partitions data off to nodes, and you can, each node of the computer will be reading the file separately, and if it's in a parallel file system, it might be a little bit faster. But it's not really a good solution to the disk transfer bottleneck.
Yeah, and so that gets back to it. So when we talk about this bottleneck, and we're going to talk about at least one strategy, but I think fundamentally, if we think through the strategies that need to be evaluated, come down to the fact that you need to limit how much disk or how much data that you need to read off the disk. Right. And that seems like really the only strategy that's going to work. And perhaps, Scott, as we get into some of the results of the research we've done here at Tecplot, you can talk a little bit about the concept of subzone load on demand.
Right. Back to what you said, you need to reduce the amount of data you read. That's the primary way to speed things up. There's really not much else you can do. And to do that, there's only a couple of ways of doing that. One is you can massively compress the file. And then, of course, you're reading less data because it's compressed. The other is you can actually be selective about what you read from the file. And that's what Subzone Load on Demand is. It says it looks at the fact that for instance, for a slice, you need to read very little of that file in order to create that slice.
Right.
You only need to read the data near the slice plane. And so if you have some sort of an indexing into the file that tells you that these pieces of data are close to the slice plane, then you can do that. You can just read those pieces of data, and that's exactly what Subzone Load on Demand is. We break the data into smaller pieces, which we call subzones. We save them in a file, and we index that file in such a way that you can selectively pull those pieces out based on certain criteria.
And we'll certainly get into the nuts and bolts of Subzone Load on Demand here in a moment. Mm-hmm. Now, as we're thinking this through, one of the key things that we need to understand is when we look at the computational environments, the codes that are being used in the data file formats, we'd like to understand, in the context of the work you're doing, what format are your data? And not use CFD here, but please, if you're not doing CFD and you're doing another finite difference or finite element model of your particular physical model of interest, really anything, what format is your data? So we're going to quickly ask the question. So if you look at your data, what data file format are you using? So this could be anything from CGNS, and again, if you're not using CFD, you're probably not going to be using CGNS data, but something to understand. Plot3D, again, a very common CFD file format. Tecplot, of course, is, as it turns out, a very common CFD file format, and it's been around for a long time. And so we have a lot of people who just use Tecplot as their format. There's a lot of readers out there that can read our formats. So, and then it looks like, if you don't know, maybe you're an experimentalist, or actually maybe you're writing your own code and it's kind of your code, so maybe there is no other. And then other.
Yeah, if you do know, if you're in the other group, feel free to go ahead and put it in the question as a question in the question box, I guess. Type in what format you do use, because we're always interested in what people are using.
Yeah. Okay. Well, it looks like we have over 70%, so we'll go ahead and close the poll, and I'll show you the results. So, of course, as you might expect with this audience, perhaps there seems to be a high number of people who are using Tecplot. ANSYS Fluent, sorry, could have put that one in there, but sure. Case and DAB files, very common. And it looks like CGNS and Plot3D. CGNS seems to be much more prevalent when we go in Europe. And Scott and I have spent a fair amount of time talking to researchers at places like DLR, MTU, Onera, and they all seem to be using CGNS. So maybe not as popular domestically. Okay. Well,
thank you, guys.
Thank you. Okay, so now let's talk about As Scott pointed out a moment ago, and I think that this Subzero Demand concept, this graphic really illustrates what we're talking about. Of course, this is an extraordinarily simple case, but I think it highlights what you really get in partitioning the domain. So if we can index a domain, decompose it into smaller domains, when we think about a feature that we're trying to render, for example, this is a contour line, but you can imagine this could be a slice or isosurface. Realistically, one only needs the data where this line is contained, which in the very simple case that I've shown here, where we're looking at 16 total cells, subzones, so to speak, you can see that in this context, we're only using 5/16 of the total data. Now, of course, the more refined you get, the smaller those little subzones, then in fact, the amount of data you load actually goes down. And we'll talk about that in detail.
Yeah, one of our goals with this is to make it sublinear, significantly sublinear, because as the data size increases, if the number of subzones you load is a smaller and smaller percentage of the total, then we can overcome that gap, that the redshift, the increasing gap over time.
So, of course, this 2D example could be extrapolated into 3D, or extended, pardon me. So again, the index decomposition can be extended, and this is an example we're looking at Isosurface. Scott, I forget, is this the 1 billion cell model?
Yeah, this was a, I think it's actually a little smaller, but it's a large ordered data, IJK ordered data in this case. And you can see on the right, it looks kind of fuzzy probably to you because of resolution, but that fuzziness, each one of those is actually a subzone, a little piece. So this is an isosurface, and you can see it's only loading stuff that is very close to the isosurface.
So to be preemptive, probably the next logical question someone's going to ask is, that's fine and well, except my data is not structured.
Yeah.
Which a lot of people have moved away from structured grids. This can be extended to unstructured data as well, and certainly we have extended this to a number, and we'll show you some test cases that are unstructured as well.
And this is not this is a standard problem for the people who write codes, is how do you break up your data into pieces? Yeah. You know, so in their case, they're trying to send them off to the nodes of the supercomputer. In our case, we're just breaking them up so that we can read them selectively, but it uses very similar algorithms.
So we're using a recursive orthogonal bisection method?
Yeah, at this point. That it could be another algorithm, but that's a fairly simple one.
So when we talk about the subzone selection interval tree and look at some preliminary results, it's been pretty encouraging, Scott. I mean, these results are pretty impressive.
Right, and so this is for the indexing. The determining which subzones you need to load. And so what we've done is created this binary tree of intervals, and this is for an isosurface or a slice, and you can actually quickly go through that tree. And so this shows how quick you can go through the tree to determine which subzones you need to load. And it's it's at least an order of magnitude faster, 2 orders of magnitude faster than if you just went through a list. And this is not that large, frankly, but you can it's a billion cells or 10 billion cells. I guess it is large. You can go through in a millisecond. So it's really not a significant amount of time to determine which cells you need.
So when we're going to go ahead and go into one last question, and then we're going to dive into the results thus far. So when you think about the visualization that you're doing today, we've seen some trends around doing that visualization either in batch, and a lot of times we're hearing, well, I do it in batch because interactively it's just not feasible. It's so slow, I just can't do it.
Right.
In fact, I talked to a group yesterday. I just don't do it anymore because it just takes too much time. So they're basically doing either pre-processing, out-of-core processing, where they'll do an extraction, or they'll take a look at one case and then do everything in batch, so they never actually have to see it. So what we want to understand from the work that you're doing today, and you think of this in the context of how you work primarily, and again, you may shift between these paradigms, but in terms of the processing you're doing today, would you say that that processing is primarily batch, or means more or less all batch? You don't do anything interactively? Is it batch processing with, like I said, a momentary, you'll go in and look at a case, get a standard view, but more or less you stay out of that mode? Do you mostly do interactive visualization and perhaps do some batch processing, but generally not a lot? Or do you do all interactive line plotting as well? And so, and I put in the last one, I'm doing 2D XY line plotting because, in principle, people doing that type of work, this isn't an issue. I mean, you can't, doing line plot batch preparation is probably not a big win,
right?
Honestly. Okay, we're at 60%, more or less, and we'll leave this open for another about 10 seconds, and we'll go ahead and show you the results. Okay, so let's go ahead and share those with you. And thank you, Brian, for putting in yours as well. So we'll add that to the totals. So you can see here quickly that most people are still doing a lot of interactive visualization and exploration with some batch processing, and there's a significant component of folks who all they do is interactive exploration. They're really not doing all this in batch. So that's good information.
Yeah.
You know. So for those people who are doing this interactively, this strategy is going to be wonderful.
Yeah.
It'll make your life infinitely easier. And that's certainly what we're trying to do. So let me go ahead and hide this. Okay. So Scott's going to walk through some research he's done. We're going to talk about 3 or 4 test cases that range from 1 billion cells to 400 million cells. Is that about right, Scott?
Oh, it looks like we have 200 million.
Oh,
200 up to 1 billion. Mm-hmm.
Okay, so why don't we actually walk through some of the results, and this is the part that I think has been most exciting, at least for me. So let's go ahead and start by looking at the test case, the billion cell test case.
Right, so this is synthetic, and this is so we could test the scaling of this approach. And as I mentioned, we want it to scale sublinearly and actually be much faster than reading the whole set, and you can see that it is indeed much faster. The green line is the Subzero Demand. The red line is our original Tecplot, and it's at least 15 times faster. But the other thing it does, which is very helpful, is it uses a whole lot less memory. And in using a lot less memory, it allows you to run it on a machine where it would not have been able to run before. Or you can run multiple cases simultaneously on that machine. So that's a very valuable side effect of this approach. This is the same case, but if you actually look at, this is where we're actually trying to determine what is the scaling. How does it scale over time? And in this case, you can see that it scales within the 2/3 in terms of the size of the data set, the number of cells in the data set. So N is the number of cells. The amount of data that you load and the time to actually generate, in this case, an isosurface, goes within to the 2/3, which is what we were hoping for. That's the theoretical maximum. By the way, if you're doing a stream trace, the theoretical maximum is into the 1/3, and wow, we do get pretty close to that as well.
So that's an important thing to point out, is that going sublinear means that as data gets larger, the effect is actually more pronounced.
Right, yeah. As the data gets larger, the performance improvement you get with Subzone Load on Demand is better.
Let's take a look at a more real case for a moment and talk about the transport example.
Yeah, so this is a generic transport aircraft, like a commercial aircraft, and it's in the landing configuration. So it has flaps and slats down, it has landing gear down, and it's in a strong crosswind. This is a finite element case, or finite unstructured grid at least, finite volume, and it uses a mixture of prisms near the wall to capture the boundary layers and TETs away from the wall. 187 million cells total. And we're going to be looking at velocity data and the volume. You can see the sizes, etc. We're going to look at the slice and an isosurface on this. And so the slice, actually the amount of complexity in the slice varies depending on where the slice is. Up near the nose, there's not a whole lot of grid, but you can see it right at X25 there in this image. That slice actually goes through the engine. It actually captures some data within the engine, inside the nacelle. It goes through the slat, it cuts through the fuselage, and those same components on the far side. So that's where the majority of that's our largest slice in terms of the amount of triangles on it, and that is and you'll see that in the results. So here is the time it takes to generate this slice, and this is not just generating the slice. This is actually the time to read the data from the hard disk and generate a slice. This is off of a standard generic hard disk drive on a workstation, a Windows workstation. So it varies from about a second up to as high as 9 seconds to read and generate the slice. And compare that to the standard Tecplot, which is about 140 seconds. You can see, go ahead and click the next one. You can see that it's dramatically faster, anywhere from 20 times faster up to 120 times faster to generate the slice compared to the standard Tecplot.
Well, it's worth pointing out, too, that standard Tecplot, based on the benchmarking we've done for a similar configuration, is basically comparable to, if not faster, than anything on the market today.
Oh, yeah, and it's not just us. We're getting the same message from those customers who've actually taken the time to do a rigorous test. And we just got another one in recently. I won't say who it is, but those customers that have taken the time to do a rigorous comparison to the other commercial vendors, it is we're pretty comparable to them in most cases with the standard Tecplot. So this represents not only a dramatic improvement over the standard Tecplot, but also over our competitors.
So in the context of memory, we see similar improvements?
Oh yeah, I mean, look, it never gets up to a gigabyte required memory. The maximum is around 800 megabytes, and it's for the most part it's down around 400 megabytes or less. And remember, this is not just the memory required for the data that's read, but it's also the code. This is the total memory used by the code, including the data. Compare that to the standard, which is up around 16 gigabytes in this case.
Right.
The standard Tecplot does not read all of the data, by the way. It only reads the data it needs, but it reads it in much larger chunks. It reads the variable for the entire zone, all 187 million cells. And so it's substantially faster. It's or substantially less memory. Again, between 20 and in this case 55 times less memory than the standard Tecplot.
And this is really important. We go back to that slide. It was like the third slide, and we talked about people looking at collections of results. Part of the motivation of this work was to figure out how to reduce memory footprint so that one could look at 100 cell models on a very beefy machine, obviously, 100 million cell models, that is,
right.
Interactively, perhaps, do a slice.
Yeah.
Which just something that we see as a huge win for those people who are looking at collections. So this wasn't motivated only by very large single solutions, but also by collections.
Right. Just real quickly, we did do a stream trace. In this case, this is very preliminary results, and it went from 170 seconds down to 2.2 seconds. Remember, this includes loading the data. Standard Tecplot is actually quite fast once you've loaded the data to add stream traces. But if you include the loading the data, it's much faster to do it with the Subzone load on demand. Next case is a wind turbine. I'm not going to go through all these details, but this is an unsteady case. Looking at the flow behind the wind turbine and the acoustics, and this is just gives you an idea of what the solution looks like. So this is a vorticity magnitude, so we're trying to capture the vortical structures behind the wind turbine. And you can see we do capture them. They get the wingtip vortex and a fair amount of wake off of the blade itself and the pylons. And so that is what we're looking at. Go ahead. So if you look at the time to do this slice, and this is actually each time step independent, you can see it takes on the order of 6 seconds to read the data and generate the slice, and it goes up slowly as the time step increases. I didn't mention it, but this case starts at about 30 million cells, and by the last time step, it's at 260 million cells. So it's an adaptive mesh refinement. Compared to the standard Tecplot, you can see it scales much better. It almost looks flat. It's almost as fast with the 260 million cells as it is with the 50 million cells, whereas the standard Tecplot's scaling not as well. Same thing with memory. You can go ahead and click through to the next ones. You can see that it's almost flat compared to the standard Tecplot, and in fact the ratio is don't have the ratio in there, but it's very substantial.
So let's look at our last example before we get into some of the Q&A, which is the trapezoidal wing.
Right. This is the case that was used in the high lift prediction workshop. It is it's a standard configuration. There's some experimental data for it. It's again a high lift type configuration. It's a wing with flaps and slats, and it's in the standard case is a half body, and in this case we've mirrored it. We've actually made it into a full body by just copying the data to the other side. Its finite elements has bricks near the wall, tets away from the wall, and uses some prisms and in between. And it's 204 million cells for the half, but in this case we're actually looking at 408 million cells, so it's almost 500,000 cells.
500 million.
I'm sorry, 500 million cells. Thank you. This is an isosurface at pressure coefficient -2, so it's a low pressure region. And the standard Tecplot was 700 seconds to read this data and generate this, and in this case it was 443 seconds for the Subzone load on demand.
And 2 gigabytes of RAM, which
and 2 gigabytes of RAM, 2.5 gigabytes of RAM, much faster, 16 times faster. Now we keep talking about how we're reading the data and generating the slice. In reality, with this technology, if we read data, we're not going to throw it away and reread it again. We read the data, and it's there, and so if we do another isosurface that's nearby, it may use the same data, and so it'll be substantially faster. But we're interested in how fast you can actually do the whole thing. In this case, get the data off the disk and render it. That's pretty fast. And a slice is substantially faster. There was a lot of data in that isosurface. It was I think it was in the 10 million cells or 10 million triangles. So this is the standard Tecplot in this case is 222 seconds. And the Subzone load on demand is 2.3 seconds, so it's 55 times faster. But we include this single-threaded Tecplot because this is preliminary results, and it's done with a single-threaded algorithm. There's no problem making it multi-threaded other than just our time to do it. So compared to the standard Tecplot in single-threaded mode, it's almost 3 orders of magnitude faster. And I think there's another thing to show you here too. Sometimes people ask us if we're going to have a parallel version of Tecplot. Well, this tells you we're very parallel. This was done on 8 processors, so even the standard Tecplot is almost 8 times faster with 8 cores. And so it is parallel now. And the standard Tecplot and the Subzone load on demand, when we make it parallel, we expect to see similar improvements.
Yeah, so this could potentially be less than a second.
Yeah.
Could be. I guess so. We can't guarantee that yet.
Until we actually do it, we won't guarantee it, but it could be.
So that's it. So that is pretty preliminary, but we are in the midst of doing this work, and we'll talk about this in a second. We are looking for people who are looking at relatively large data who would like to participate in some of the early testing of this technology. we'll have an opportunity here in a moment to ask questions. Before we do that, though, perhaps it's worth just a quick summary of the work thus far.
Oh, sure. I mean, as we've mentioned, we get dramatic reductions in memory requirements. Amount of reduction depends on the size of the data. The least reduction we got was for the wind turbine, where the data started out at 30 million cells. And so you don't get a whole lot of reduction at 30 million cells compared to what you get at 300 million cells. Right. But factors of 4 to 50 less memory was used. And the scaling is n to the 2/3 for the isosurfaces and slices, and it's n to the 1/3 for stream traces. That's good. That means going into the future, we're going to continue to see improvements. And the speed improvements are even more dramatic than the memory improvements. 15 to 120 times faster for the large cases, even 3 times faster for the smallest case. And so substantial improvements. And we didn't talk about that, but we're focusing on the slow speed you get from reading the data off the disk. But in fact, there are people who are wanting to run the data, read their data over the internet, for instance. They have a slow, very slow connection. And for them, they may still have a network bandwidth bottleneck. But the nice thing about this approach is that it will still benefit those with the network bandwidth bottleneck. Not only those that are using, that are constrained by their hard disk read speed. We got a question that asks us to please explain the parallel features of the standard Tecplot.
Well, let's try to grab that one, and we'll grab that in about 1 minute. So hold on, Tom. We're going to get to that question, I promise. So just to be very clear here, the benefit on the slower network, or even if you have large remote data, our intent is to have in the future a subzone server of sorts, in which case Tecplot will be operating in this more of a client-server model, although we may not call it that. It's hard to say.
Yeah.
But that is certainly our intent into the future. And we're pretty excited by this research. In fact, we've had an opportunity to show a couple of folks at the ASM show recently, and they were blown away by what we were able to do. So the question we have for you, if this technology looks interesting to you and you'd like to be involved in some of the early testing, please contact, and we'll leave this up for a moment, so we'll have this during the Q&A, but we would absolutely love to have 10, 100, 1,000 people who want to evaluate this technology to help us refine it, make it better. Because we can only test the data we have, and we don't have an infinite set, so we may be missing something. But this is a real important technology for us, so we're quite interested. At this point, we'd like to open it up to questions. So again, there's 2 ways to ask a question. I would recommend, given the number of folks online, that perhaps just typing into the question and answer box, and we will start to go through. So let's see. We'll give people an opportunity. We have about, based on timing, we have about 5 minutes or so for questions, so we'll try to be judicious in our answers. But if you have additional questions, you can always email us post-webinar, and we'll certainly answer them at that time. So let's actually start with Tom's question around the parallelism in standard Tecplot.
Sure. Tom, this is we use a shared memory parallel. So this is if you have a computer with multiple cores, which is almost all computers now, or you have multiple processors, multiple cores, then we use multi-threading, and those threads are in a thread pool, and those threads are activated as they're needed, and they sleep when they're not needed. And this is important because every once in a while somebody says, I'm watching my performance monitor, and you're only using one CPU or one core. And at the time they were watching it, we probably were only using one core because it wasn't doing something significant. But then if they had done a slice, they would have seen it jump up to using 8 cores if they had 8 cores, and then drop back down to using 1 core as soon as it was done. And that is we think that is an advantage over what a lot of other folks do using, for instance, MPI or some of the message passing protocols, because with the message passing protocols, often it just sits there and spins, and the operating system has to wrest control away from the application in order to make it available to, Word or Outlook or whatever else you're running on your computer. So that's how we do our parallel. We use multi-threading with thread pool.
There was a question about when this technology, is it available in the current version of Tecplot? This work is still preliminary, so as I mentioned earlier, we are definitely looking for people to help us test this technology. Our intent is to have some implementation of Subzone Load on Demand and other strategies for large data performance in Tecplot by the end of the year. There's also, for those of you who are current Tecplot customers, we will be releasing the next generation of Tecplot 360 this year as well, built on new technology. And that's actually slated for the first iteration of that might be as early as May, maybe even earlier than that, depending on how much progress we make in the next couple of months. So stay tuned. If you're interested in being part of the beta testing program on that as well, we'd love to have you. So again, email Scott or I, and we'll put you on the list and get you access to that technology.
And that will have some performance improvements, but it will not have the Subzone Load on Demand at that point, in most likelihood. Mm-hmm. It'll be later in the year.
There's a question about does this loading improve the RAM usage for generating animations? And in fact, I guess, Scott, we weren't explicit about it, but the test case we use with the wind turbine, in fact, is to create an animation.
Yes, yeah, that's an animation. And in fact, on the animations, it can be even more dramatic because you can throw away the data from earlier times, and generally speaking, you're not sitting there and adding more slices on the same time. You create a slice or an isosurface and you animate it through time, and so it actually reads a lot less data. So the performance improvement could be very dramatic with animations.
Mm-hmm. There was a question about MATLAB file format. We do have a .mat loader. In fact, there was a recent blog posting. If you go to Tecplot.com and go under our blogs, there is a way to load data from MATLAB directly into Tecplot for those people who are looking at it. We have time perhaps for one additional question. So if you have a question, go ahead and type it in now. We have a couple of questions from earlier, so I'm going to go back up. And there was a question specifically from someone who may in fact not be online at this moment, but had to do with blanking technology and being able to, for example, only load a particular type of data. And they were thinking more in the context of particle data. Mm-hmm. Particle data, unless each particle were a zone, I think is kind of an odd case in how this technology might work. But I think a core blanking capabilities allow us to do, in effect, one of the questions they really want to do is, hey, I've got some particles that are real, so to speak, and some are virtual, and like to turn the virtual ones off. That's pretty easy to do.
Right. You can either do that with blanking, or you could do that with, if they remain virtual particles the entire time, you could just put them in a separate zone and then turn that zone off.
Okay, our last question has to do with when the next version of Tecplot 360, this next generation tool, quote unquote, will be available for testing. So the short answer on that, for those people who are interested, we have a beta coming out probably in the next 2 to 3 weeks that would be available for testing. So if you're interested, just drop me an email, or you can actually contact us through the website as well. Well, Scott, thank you for another entertaining webinar.
Thank you, Darrell.
Thanks, everyone, for sitting in with us. Hopefully this was an interesting discussion, and I'm sure there will be some questions that will come along. Again, feel free to contact us. Or if you'd like, we can continue this discussion via Twitter, or you can contact us via Tecplot.com. We have a YouTube channel where we have a number of examples of this, and we also are on Facebook. Thank you very much for everyone for sitting in with us today. The recording should be available sometime in the next few hours. Thank you very much.
Thank you.